Hey everyone, this is Juno in another video of Why Did We Care? For those of you who might have missed the first video, this series puts into historical context the mathematics that we learned today. There's an argument made recently popular by German-born Dutch mathematician Hans Freudenthal that mathematics is an inherently human and social activity in nature, at least when used in the capacity to organize, quantify, predict, and model the world. Probing into the genesis of a mathematical idea offers insight into the context and needs that give rise to these mathematical constructs that we study. Additionally, knowing what tools were available at the time these things were invented helps us understand the development of that mathematical idea. And it also offers additional insights into the intuitive way that we should actually be thinking about these objects. So today's topic is on linear algebra. So this is a topic that's covered in, first year, second year university, depending on where you are. And it's very, very crucial to almost anything that you do. Statistics, computer science, definitely, higher mathematics, engineering, really anything. It's really a very practical subject to learn and understand because it is very useful in a lot of different areas. Last time, we covered high school geometry, specifically Euclidean and coordinate geometries, so I wanted to touch on something that most students cover in depth during university. Naturally, historians of mathematics, yes, they exist, differ on what events they believe contributed the most to the history of linear algebra, and there's a number of papers that promote different views. But the general consensus is that there are two major, distinct, but related ways to view linear algebra. One can think of linear algebra as sort of the study of linear systems of equations and their solutions. And historically, this is exactly how linear algebra came to be. The other point of view is to consider linear algebra as the study of vectors, vector spaces, and linear transformations, which are mathematical constructs that can be described in a formal, axiomatic way. My personal viewpoint is that pedagogically, linear algebra should be taught through the latter viewpoint, starting off with vectors and vector spaces, and then understanding matrices through linear maps. However, I admit that linear systems of equations are far more concrete and familiar to students when first introduced to linear algebra, and it's a strong motivation for students to continue on in the subject. Since I'm talking about the history of linear algebra today, I'll be focusing mostly on how it was developed as mathematicians studied and tried to understand linear systems of equations through the centuries. The core idea that will be somewhat central to all of this will be Gaussian elimination, or perhaps better known as row reduction. I imagine most university students who've taken a course in linear algebra are more than acquainted with row reduction. In fact, you're probably sick of it by now, having done both manual computations and computations with a computer through MATLAB countless times. But did you guys ever think about how row reduction was discovered in the first place? Why does row reduction always give an answer to whether linear systems of equations has a solution and tells us if it's unique or if there are infinitely many of them? It might seem obvious to you guys now, but given that it took decades, centuries of work even, it really isn't if you think about it. I'll start off by talking about how Gaussian elimination was developed in Western Europe. It was actually the Chinese who discovered this algorithm first, all the way in 200 BC, but I'll talk about them at the end since they don't really fit into the modern narrative, and their solution to linear systems of equations that developed into Gaussian elimination is admittedly different in some aspects than what we have today. So during the Renaissance era, sometime in the 1700s, early 1800s, the determinant was independently developed both in Europe and Japan. Japanese mathematician Seki Kowa developed his version of the determinant while trying to find a method to solve a nonlinear systems of equations. Gabriel Cramer, the same mathematician who developed Cramer's rule, developed determinants as a way to specify a solution to a system of linear equations based on the coefficients. In particular, the notation that Cramer used at the time was actually very crucial. Using symbols such as x or alpha to describe an unknown fixed quantity was in use as early as 300 BC by Greek mathematician Euclid, the very same Euclid who made the treatise The Elements. But their usage really wasn't modernized until the French mathematician Viet did back in the 1591s, so a fair bit earlier than when determinants actually came about. The subtleties are a bit difficult to convey in words, but the way their notation was structured naturally sort of shapes how these mathematicians came about thinking about the determinant. For example, let's consider a very basic or simple usage of notation, sine to the -1 of x. Normally, most students will have learned by this point where they're introduced to this notation that, for example, 2 to the -1 actually means 1/2. You take the reciprocal of the number of the exponent that you take. But for some odd reason, sine to the -1x is not 1 over sine x, but in fact, it actually means sine inverse, or arcsine x is the other notation that mathematicians use. This confuses a lot of students in high school, and quite frankly, I don't blame them. Particularly since sine to the 2 of x is the same thing as sine of x all squared, or sine x times sine x. That's just wildly inconsistent. The notation stems from the fact that functions use this kind of system. For example, f to the 2 of x would mean f of x, and f to the -1 f cubed x would be actually f squared x. They cancel out the same way that numbers and exponents would cancel out using exponent laws. So the notation that we use for functions was adopted into the notation we use for trigonometric functions, but they just don't make sense in the same way anymore, because we use them as functions and then we also treat them as numbers. So we're mixing up these two systems here. There's actually an argument going on in the mathematical community that the entire system of notation that we use for trigonometric functions right now should be completely scrapped and changed so that it's actually consistent with the function system that we use, not the exponents, the function system. Of course, we could just move it to the exponent system as well. I really don't care either way, but I would actually really love it if they were consistent with the notation that you use for trigonometric functions. And if they do move it to one way or the other, they would use, instead of sine inverse, arcsine. And in fact, you'll see most mathematicians strictly use arcsine only when talking about the inverse of the sine function. But I digress. Without delving into the details of the notation that Cramer actually used, the notation that Cramer developed allowed him to articulate the determinant to be more like that of a mathematical object, a quantity that can be associated to these systems of equations. Associating a simpler object to a more complicated system is very beneficial because this allows us to study the simpler object and gain insights into the more complicated system. So, for example, in this particular instance, the determinant, we're able to compute a number, and understanding this number allows us to understand something about the system of equations. And it's easier than trying to just solve the systems of equations directly. So historically, determinants were developed to express solutions to linear systems of equations in terms of their coefficients. But it was not the case that determinants were developed or emerged with the explicit goal of being able to determine whether a system had a unique solution or not, which is how students sort of use them today, or how they're first introduced to students in math classes. I admit that it's useful pedagogically to sort of reinvent the determinant as a tool to figure out whether linear systems of equations has a unique solution. But back in the days when Cramer worked with determinants, he didn't actually think about this sort of way of thinking about determinants. He was just trying to make the linear systems of equations more workable, simpler, break it down to a single number that helps him understand more about it. But today, when we're talking about determinants, we sort of reinvented it completely and changed the original purpose of the determinant so that it helps us understand whether a linear system of equations has a solution or not. And I think that's fine. I think that's very useful for students to think about determinants in that way. Just that it wasn't historically how the determinant came about. So the determinant is an important development in the history of Gaussian elimination. Another development occurred in France in 1750. Leonhard Euler questioned whether a system of equations with n unknowns always had a unique solution. And naturally the answer is no. And Euler showed us that this was the case with a specific counterexample. 3x minus 2y is 5, and 4y is equal to 6x minus 10. Not all math needs to be complicated. Visually, it's also easy to note that this can't be the case by considering the fact that these linear systems of equations, at least in 2 dimensions, are just lines, and that it's easy to have 2 lines that are parallel, and that the intersection points are solutions. This fact that Euler discovered becomes significant decades later. In 1811, Gauss developed a method to best approximate a solution to an indeterminate system of linear equations with 12 equations and 6 unknowns. I don't know exactly what this method was, but it was during the time that he developed the method or algorithm that we now call Gaussian elimination or row reduction. I'll probably just use Gaussian elimination because I think that sounds way cooler. It's also during the time that matrices hasn't really been developed yet, so it makes more sense to call it Gaussian elimination. And I, tribute the mathematician that actually came up with this. Gauss's work required a complete understanding of the conditions in which a system had no solution, a unique solution, or infinitely many solutions. Here's actually an explicit quote from his work, Theorio Modus. I probably pronounced that terribly, but it's also known as the theory on the motion of heavenly bodies moving in conic sections. So if matrices weren't involved in Gaussian elimination, where and when exactly did they come up? The term matrix was actually coined in 1850, almost 40 years after Gauss developed Gaussian elimination. And it was discovered or invented by James Joseph Sylvester, the same Sylvester whose name comes up in Sylvester's law of inertia. In 1857, Sylvester's friend Arthur Cayley, the same Cayley whose name shows up in those math contests we have in Canada, published his treatise on the theory of matrices. Cayley introduced matrices from the natural point of view of, again, systems of equations, but later developed matrices as a mathematical construct that can be added, multiplied, subtracted, and inverted. In 1875, Frobenius offered a definition for linear dependence and independence that works for both equations and n-tuples or vectors. In 1888, Peano, I don't know how to pronounce his first name, I'm not even going to try, formalized the first modern definition of vector spaces and linear transformations. But unfortunately, his definitions actually didn't become popular until 1918, when Weyl basically repeated Peano's work in his book Space-Time Matter, and articulated an important relationship between viewing linear algebra from systems of equations to vector spaces and linear maps. Alright, so we talked basically about the important things that almost everyone's sort of seen in a linear algebra course. Determinant, matrices, linear independence, vectors. But I haven't really talked about the algorithm that I really want to talk about in this particular video. Gaussian elimination explicitly. Gauss was working to determine information about the elliptical orbit of an asteroid named Pallas, which was discovered in 1802 by Heinrich Olbers. Actually, at that time, Pallas was considered a planet and not a meteor or asteroid. Using a set of observation measurements, he tried to determine the eccentricity and inclination of the orbit of Pallas. This information was then arranged to form a least squares problem, and then in order to solve it, Gauss developed Gaussian elimination as an algorithm to solve the system of linear equations that he came up with. It had 11 equations and 6 unknowns. He actually originally had 12 equations, but one was discarded because the observations seemed wildly inaccurate. His 1811 work, Disquisitio de Elementis Ellipticis Pallidus, I have no clue how to say that, gives a detailed explanation of his overall work in developing Gaussian elimination. So that's basically how Europe developed the algorithm Gaussian elimination to solve linear systems of equations. However, before Europe came with all this, nearly 2 millennia earlier, China had already developed its own method of solving linear systems of equations. The 9 chapters on mathematical art is an ancient Chinese text comprising of 246 problems and solutions, and it's dated back all the way to 221 BC. The original text of this work was actually burned during Emperor Qin Shi Huang's reign, the one credited with the unification of China and the creation of the Great Wall of China. The problems in this text arose from typically real-life scenarios such as trade, commerce, taxation, distance rate time problems, and field measurement. For linear systems of equations specifically, these kinds of problems actually came from mostly agricultural contexts, so farming, raising crops, etc. In chapter 8 of the book, there are 18 problems, all of which deal with linear systems of equations, and 13 of those came about from quantities of livestock or grain. The others consisted of combinations of different types of coins, weights of various animals and livestock, and the amounts of waters that had to be shared between different families from the communal well. To solve these problems, China developed its own form of Gaussian elimination. However, do note that the method that China came up with was constrained to only integer coefficients. Furthermore, these problems only ever had at most 6 different kinds of unknowns. While this theory was developed far in advance from Europe, keep in mind that Gauss and all the other mathematicians during that time worked in contexts that required non-integer coefficients, so fractions, real numbers, maybe even complex numbers. And not only that, they also discussed not only the possible solutions, but also what conditions arise for each possibility. The Chinese texts were driven by pragmatism and real-life examples, as well as inductive logic, whereas Gauss's work was more theoretical in nature, relying on the deductive logic system that the Greeks introduced back all the way in 300 BC. This contrast is evident even today in students, where they want to sort of see the practical uses of the theory that they learn in class. Merging the two together is not easy, but I hope you guys, my viewers, can appreciate the work that went into developing what linear algebra is today. Looking back into the past helps us progress forward into the future, helping us develop practical and theoretical understandings of key ideas in mathematics. This was another video of Why Did We Care? See you guys next time.